Awesome. Perfect. So, hello everyone. Happy Friday, and thank you for staying with us and joining the last presentation. Uh, it's a Friday afternoon, and people have so many things to do. At least in Toronto, it's Friday afternoon. I know in Europe, it's almost night, I guess. So, yeah, today I'm going to talk about innovations in efficient training, tuning, and serving large foundational models. I personally mainly tried the techniques with LLMs, but I think if a model is, multimodal, the same techniques can be applied. And basically, the workshop will be very hands-on in a sense that I'll explain things briefly. I have references to the papers, blog posts, GitHub repos in the slides that you can access later, and hopefully you can take that and basically go fine-tune, serve basically your foundational model after the presentation. I hope it's going to be useful for you. My name is Ali Reza Darbahani. I'm an ML platform engineer, also known as MLOps at Bensai, and happy to be here. Feel free to ask questions. All right, let's get started with the first slide. So why do we need efficiency and scale? It might be obvious by now, like since you guys have tried to use LLMs at work, for your side projects, just do cool things with it. You usually have two options. You either buy APIs, basically you get charged based on your usage and you call the API of OpenAI, or some hosted model on Microsoft Azure, or any of the other cloud/API providers such as Cohere in Toronto. And that's good. That's very easy in a sense. But the problem is sometimes it's like it's costly to use APIs, right? Like if you have a lot of data, if there is no big business values coming out of basically making money coming out of calling APIs, you might want to try the techniques such as hosting your own model, take an open source model, fine tune it on a specific task, host it yourself. Or maybe you even have some data governance and privacy issues and you don't want to, or you can't use the APIs, although they provide in their contracts, they provide all the, they comply with all the data governance and security most of the time. But let's say you're kind of nerd enough to just go and fine-tune train your model. So the issue with it is it's too costly, right? Like GPT-3 cost estimation of training it, I think for one round, is basically roughly for 4.7, like 5 million to train. Also, for a lot of models these days, they're large enough. If you have like I would call them conventional GPUs, like GPUs with 16 gigabytes of RAM, you can't really, without doing any improvement of memory efficiency and stuff like that, which I'll get into the techniques in a bit, you can't really load the model on a single GPU, right? Like if you are on some cloud services and you just want to have a VM with NVIDIA T4 or V100 GPU with 16 gigabytes of RAM, your model doesn't even fit, let alone you start the training and also have like a data set with larger batches. Also, the same thing is true for inference and serving the model. If you, again, don't use any technique, like you can't load the model on a single GPU. And if you want to use multiple GPUs, you need to know how, right? And basically, other drawbacks of, not applying efficiency and scale, like not using the techniques, is, of course, it takes a long time to train for fully fully tuning one model. Also, the model have a very low throughput in production if it just deployed as a bare-bone model. You just download it from Hugging Face without using any of the techniques, as an example. So when you want to just get inference, you don't have that scale. You just send it a prompt. Let's say it's a text generation model, right? So basically, you want the answer under a couple of seconds, right? Like you don't want to wait 5 minutes to get your answer back. And also, the accumulation of all of these reasons is basically, the result is, if we don't have these techniques and if we don't use them, then Gen AI, large language models, it will be less accessible for people and it's less democratized. So basically, you always rely on big players such as OpenAI, Microsoft, Google Cloud, etc. So I had a request to create this basically slide, and I think it's kind of relevant and useful. So before we get into the techniques, let's discuss, the difference between fine-tuning an LLM versus combining an LLM with I would call it SLM, like small language model. So what does fine-tuning mean, right? Like, by now, probably a lot of you know what it means, but basically, you have a pre-trained, let's say, large language model, and which is trained on a big data set on many generic domains. For example, like the data set, the corpus had like data about legal, animal, biology, its history, etc. Right? Like the available APIs we have through OpenAI, it's basically trained on the internet knowledge. But let's say at work, you have a very specific data set and you want to train your language model basically on a specific domain and knowledge, and you have the data set for it, right? So you basically do fine tuning. You don't start from random weights basically initiated. Your model is pre-trained. It already has knowledge. And basically, you train a subset of the weights. Or if you do full fine tuning, you give it your data, represent your data to the model, and basically you train the model. So that's fine tuning. There are pros and cons for doing that, but we also have this method of combining large language model with a small model. And the way it works, and small models these days basically are not that small. Like it can still be a transformer based, such as, transformer based model. And basically you give it your data set, you train it, and then you interface it with your language model. So your inference data goes into the small model. The output will be the input, for example, of the LLM. And there are pros and cons. The pros are fine-tuning. It works well on the small data sets. There is less complexity compared to the interfacing models, because the opposite, you need to know how to interface these two models, how they work. The cons of it, if we don't use efficient techniques, then it's going to be expensive to fully fine-tune a language model, or even not fully fine-tuning is still time and money consuming task. And also one issue with LLMs, like they are not a good fit for every single NLP task. So sometimes the smaller models perform better, or you don't know how to represent the data in a way that the language model would be able to perform better than the smaller existing models on that NLP task. So that's the cons of it. And combining models, there are pros and cons. The pros are can be used for baselining, in my opinion. You can try this method because it's fast. You train a small model, you interface it with your LLM, you get some performance as your baseline. Basically, it's useful for tasks that LLMs are not good at, such as, I did some Google search on it. Basically, tasks such as doing mathematics, I guess, and also working with some structured data. This method works relatively well. Also, it's very cheap to fine-tune a small model. You take the pre-trained model, you give it your data set, and you just tweak the hyperparameters, and hopefully you can have a good results. And then you combine it with LLMs. You can benchmark it and see if the outcome is satisfying or not. The issue with it, you need to do some magic, like data engineering, software engineering magic. You interface the models, you need to know what is the best way to interface them, and then improve the output of these hybrid models in a sense. And you also need more data. But now let's get into the techniques I want to talk about today. Here in this slide, I'm going to go over like what I will cover and what I won't cover, basically. So by now, I think everyone is kind of familiar with prompt engineering techniques, few-shot learning. These are the techniques you can even easily use on OpenAI API, even the ChatGPT UI. You can train your own GPT in a sense by few-shot learning. The original model weights usually don't change. They are sitting behind the API, and I don't think OpenAI has this mechanism that personalizes the models a little bit. But you do prompt engineering, you improve your outcome. If it's a like a generative API, if it's a chat API, there are also few shots learning techniques. I just heard like Dennis talked about RAG, and that helps with getting better performance out of the LLM APIs with your data, with your documents and stuff like that. But today I'm going to focus on techniques such as distributed training, quantization, and low rank adaptation. And there are other techniques that I won't get into as well. So let's get into it. So an overview of methods and frameworks. Here, first I want to explain what the parallelization techniques are and what do they mean, because basically half of the content is around like a framework that is using parallelization along with a lot of other techniques to provide scale and efficiency for training, fine-tuning, and even serving large foundational models. So let's get into the definition of each one of these names here. So we have a concept of 3D parallelism, which means basically we use all three together to have an efficient, also a scalable way of training the model, which means the combination of these three. So let's see what DP, or distributed data parallel, is. DDP or DP. Basically, when we use DDP, the same setup of the model is replicated on multiple devices, as an example, like multiple GPUs. And each one of these replicas getting a slice of data, which makes sense. You have a data set, you put it into batches, and you distribute it across multiple devices, and the processing is done in parallel, and all setups are synchronized at the end of each training step, because you want to do a backprop based on each one of these batches went through different devices. That's one dimension of parallelization. It's very, very common. Even for smaller models, it will speed up your training, because you take your data, put it into chunks, and you have multiple devices for that you can basically, it's parallelizing the data going through the model layers. And of course, it's going to speed up the training. So the tensor parallel is different. Now, like, you're dealing with basically tensors and the model, not just the data itself. So each tensor is split up into multiple chunks. So instead of having the whole tensor residing on a single GPU, each shard of the tensor resides on its designated GPU. During processing, each shard gets processed separately, and it parallel on different GPUs, and the results are synced at the end of the step. So basically, your tensors are broken down, like different chunks go to different devices, and at the end you have like a synchronization step that the algorithm is implemented by the framework you are using. And then we have pipeline parallels. You put your models into layers or group of layers, and each device basically gets a subset of that, and the training happens across multiple devices. And we call that pipeline parallel. So these three parallelization can be used at the same time. I have a URL here. You can go and learn more about like the details, what they mean, how they happen. There are like visualization in there, which you can read more about them. All right, now let's get into the framework I want to talk about today. It's called DeepSpeed. Probably you have heard of it. It's backed by Microsoft now, and it's open source, so you have access to the source code of any of these algorithms and techniques. There are multiple papers that are the beginning of the algorithms they have implemented. So I'm going to explain some of these now. And so basically, DeepSpeed is a framework. There are groups of algorithms, which they call them stages and strategies, and some strategies have stages. So for model parallelism, both for training and inference, I just explained how it happens. The implementation detail basically is available in DeepSpeed documentation, the API. You can go and look into the code. Basically, I just want to high level explain these bullet points and what they mean. And feel free to ask questions. And after the presentation, we can go over it. So model parallelism, I explained that. Although there is another aspect called zero redundancy optimizer, also known as zero. And there are like 3 stages of zero algorithms, which I will get into the details a little bit of each one of them, the definition, and roughly how DeepSpeed, benchmark them, and how much memory efficiency they got out of using those stages. So the first one is probably 0, 1. They numbered in order. So 0, 1 is about like partitioning the optimizer state of your model. And as I explained, you partition it, you send it to different devices, and then the results is kind of synchronized at the end of each step in your training. So the memory reduction gain of using the 0, 1 is basically DeepSpeed benchmark that you get something around like 4x memory reduction with the same communication overhead between devices as the distributed data parallel. So this optimizer state partitioning doesn't really have a negative impact if you're already using distributed data parallel. But it reduces the memory footprint when you train a model. Then we have 0, 2, which is basically you also partition your gradients. DeepSpeed claims there is like 8x memory reduction. It's a bit debatable, like some of these numbers, but apparently they had the knowledge to fully optimize the algorithms and their implementation, and that's the best number they could have gotten. And also we have stage 3, which in addition to partitioning the optimizer state as well as the gradients, you basically partition the parameters as well, parameter of your model, the trainable parameters. It basically, the memory gain, the reduction of memory usage is linear with the number of devices you have. So for example, because you basically chunk your parameters, put it on different devices, if you have 64 GPUs as an example, you get 64x memory reduction. However, stage 3 has 50% of communication overhead increase. So you get memory efficiency, but you would lose basically some time because of the communication overhead between these devices. It's not significant if you have a really large model. That's the only thing one of the most important algorithms you would try. Then DeepSpeed also extended these 0 algorithms. They call it offload. So basically, some of these memory footprints, they have algorithms that offloads the data on CPU memory. So in this case, you would have some GPU memory released. The only downside of that, so it unlocks you to basically, they have actually their offload mechanism. It even offloads the memory to the data to the high performance SSD hard disk with NVMe2 communication links that is much faster than regular SSD hard disk communication, but again, like it's slower than doing all the computation in the GPU. However, it unlocks you to offload your memory to the disk, and they claim that it enables you to have like an infinitely large model because you just basically offload your memory to the SSD and read them back when you need to. just using the algorithm. So they have offload. If you look into it in the future, that's a nice addition to their framework. Also, I saw something a couple of days ago. They also support the mixture of experts architecture, so which you have a group of experts model, and a model that basically decides on the importance of the output of the experts, and it just so basically the only difference is they support this architecture as well. Like you can use DeepSpeed with mixture of experts architecture. And on inference side, though, they have done some innovation recently. In addition to model parallelism, they added MOQ, mixture of quantization. And quantization, basically, high level, it means it's a process of reducing the precision of the numbers used to represent model weights. For example, a lot of PyTorch models, at least I know, they are in 32-bit floating point precision. So basically, quantization means you reduce that to 16-bit or 8-bit floating point precision. This way, you gain some memory efficiency. The amount of memory you need to load the model reduces by halving those precisions. The downside of it is if you just do naive quantization, you will lose some performance of your model, some accuracy, because the floating points are not there. So what the mixture of quantization mean, basically, the approach is the algorithm applies different levels of quantization to different parts of the model based on the sensitivity to quantization or their importance to the model's performance. So you don't have a single quantization applied to all components in the architecture of your model. It's more of like based on the sensitivity and importance. So like there might be different level of one part might be 32 floating point, the other point might be 8-bit or 4-bit floating point. So for inference, the innovation, like they added a feature called like FastGen, and they have a paper for it. So they combine the model parallelism, MOQ, and a bunch of other things which I will explain in a bit, as in that paper as a whole thing for improving the performance of the large foundational models on the inference side of things. Basically, the next technique they added is basically blocked key value caching. And what it means is in transformer architecture during the generation in decoder, we actually just want to calculate the attention for the new tokens in the decoder. Why? Because since the decoder is causal, which means the attention of the token only depends on its preceding tokens, at each generation step, we are recalculating the same previous token attention when we actually just want to calculate the attention for the new token. When we use block key value caching, KV caching, this is where the caching the previous key and values, and we can focus on only calculating the attention for the new tokens. So it kind of optimizes the original architecture of the transformer models for inference. There's also continuous batching, which is a way of smarter dynamic batching for the inference. So it provides fine granularity, scheduling, and optimizing memory efficiency. It provides iteration level scheduling. Basically, so when your request comes in, like it has a smarter way to, batch things together for inference. And dynamic fusing basically is dynamic split fuse is basically it uses composition and decomposition of parts of the transformer architecture to improve the throughput performance of the model. They're all explained in the paper, and you can go and read the details. But honestly, like you can try out the algorithms without really trying to understand all the math behind it, unless you want to do research on it. So I didn't really go in deep into the split fusing. I just tried to understand the definition. All right, this is DeepSpeed. This is basically enabling you to leverage multiple GPUs, multiple devices, with a little bit of, improving the memory efficiency, and reducing the communication overhead when you do distributed computing across GPUs to help you to train your model. There is another technique that can also be combined with DeepSpeed, zero algorithms, that is called parameter efficient fine tuning. So apparently there is so many algorithms for parameter efficient fine tuning. It's a generic term. If you look at this photo, and there is a paper that reviews available techniques, pros and cons, and the use cases you could use each one of these, which I have a link here. There is also a Hugging Face framework called PEFT, parameter efficient fine tuning, which supports many of these algorithms, and basically, in a sense, adapted some of these models. It has instructions how to make adapters for any PyTorch-based model, at least. And I'm going to explain the PEFT framework, which is really easy to use, especially for the models that are already supported. And I'll get into what these algorithms mean, as well as some memory efficiency gains here, which we can get into in a couple of minutes. So PEFT framework. As I mentioned, it supports different algorithms, but today I want to explain the low-rank adaptation, or LoRa. There's also QLoRa, which is quantization plus LoRa. And then also, as I mentioned, PEFT can also be combined with DeepSpeed. I will explain why. There is no conflict or much of overlap between the PEFT and DeepSpeed framework. So low-rank adaptation. So low-rank adaptation leverages low-rank matrices to approximate the changes needed in the model's weights during fine-tuning. Instead of updating all the parameters of the model, LoRa introduces trainable parameters that are much fewer in numbers. Basically, it injects the parameters into the layers. And these parameters are used to compute updates to the original base in a low-rank subspace, and significantly reducing the number of parameters that need to be learned. If you look at the code and examples for creating adapters, it's really easy to understand the technique itself, because you see, like, you inject those new weights and use it for fine tuning, and basically freeze most of the pre-trained weights. So basically, you reduce the number of trainable parameters of your model by using low-rank adaptation. Quantization, as I mentioned, the naive and high-level definition is you go from the higher floating point and trying to project your pre-trained model weights into a lower floating point precision. So basically, it reduces the amount of memory you need for doing fine-tuning or serving your model. So it's good because basically, if you go from 32 to 16, you get 50% of memory efficiency here. And PEFT on the quantization side basically uses these library called bits and bytes. It takes care of the quantization, and you can quantize your model all the way down to 8-bit or 4-bit quantization, which gives you a lot of memory efficiency and memory gain. If you look at these examples here, for 3 billion parameters here, the big science, the full fine-tuning needs 47, 48 gigabytes of GPU memory. If you use LoRa, of course, it depends on your configuration. I think maybe this was the best they could have gotten. I don't know the details of this benchmarking, but it went down to 14.4 gigabytes of GPU, which means if you have a conventional GPU, which is like 16 gigabytes of RAM, you can load this model, do fine-tuning, or use it for inference and serving. And of course, as I mentioned, you can use it with DiffSpeed. So if you do that, your GPU memory requirements or needs will go even further down. You can see it for other models as well. You see that the 12 billion, you get OOM, out of memory error, because your model doesn't fit into one GPU. If you use LoRa, you get much more improvement. And if you use DiffSpeed, you're probably good to go. I think this 22 gigabytes of GPU RAM would fit into an L4 GPU, which has 24 gigabytes of RAM. So you don't even need A100 and H100 GPUs, which are really expensive ones, and they're on high demand, and it's hard to get your hands on. I think that's pretty much it. I just want to conclude that we went over the importance of why we need why we need memory efficiency in fine-tuning and serving of the LLMs, because of the cost, of the accessibility, and also if you have some requirements that you can't rely on using APIs, or you just want to play with things, using these frameworks and techniques is going to be really helpful for you. That's pretty much it. I would like you guys, if you are interested, you want to discuss this topic or any relevant topic, this is my contact. That's my LinkedIn here and my email address. Feel free to reach out. I will be happy to discuss it, help. We can go over some papers and contents together, because this is a topic I'm really interested in. I can actually, I'll be happy and open for any discussion. Thank you so much.